This is section 12.8 of the textbook, which is on cylindrical components. The equations for cylindrical components are on your equation sheet. We have an equation for the position, for the velocity, and for the acceleration. When you read through section 12.8, you will see that they start off talking about polar coordinates, because if you have motion restricted to a plane, you can use polar coordinates instead of cylindrical components, because this is what you get when z is equal to 0 and not changing. So then z dot would be equal to 0 also. So for polar coordinates, we have a radial coordinate and a transverse coordinate. The radial coordinate r extends outward from the fixed origin to the particle. So you start at the origin, you go to the particle. This direction is the radial direction, and for polar coordinates, our position vector only has a radial component, and the magnitude is r, which is the distance from the origin to the particle. So for polar coordinates, for the position, you never have a transverse component. The transverse direction is perpendicular to the radial direction. The positive direction is the direction of the increasing angle, which is going in the counterclockwise direction. Okay, so then to take the velocity, to find the velocity, we can always start with a position vector and take a time derivative. However, remember that when you take a time derivative, you have to take a time derivative of the unit vector as well. This did not matter for rectangular coordinates because I hat, j hat, and k hat never change direction. The magnitude of a unit vector does not change, but the direction may change, as we saw for normal and tangential components. So the direction of r is changing as the particle moves, and the direction of theta is changing as well. They're going to talk about cylindrical coordinates at the very end of this section before the example problems. When you have a z component, so when you're looking in 3 dimensions and using cylindrical components, the z component is just like what it was in rectangular coordinates, and so the direction of the z coordinate is not changing. So we have for position, z pointing in the z direction. You take a time derivative, the direction of the unit vector is not changing, so now we have z dot pointing in the z direction, and then z double dot, so this is just like how it worked for rectangular coordinates. So the z part there is easy. When we take a derivative of position here, we need to take a derivative of the unit vector. So we must use the product rule. So we have r dot pointing in the radial direction plus r times the time derivative of the unit vector u sub r. Now, they're going to show you how to take that time derivative here in the textbook. But remember, in a previous section, we looked at this handout and we said that if you write, and you can write any unit vector like this, well, I suppose as long as it's in the xy plane. So a 2-dimensional unit vector you could write like this. And then when you take the time derivative, what you have in parentheses here is another unit vector. And if the initial unit vector is pointing like this, after you take the time derivative, the new unit vector is pointing at an angle of 90 degrees to the initial unit vector, and then you multiply it by theta dot. So hopefully you can kind of use your intuition to figure out what the new unit vector would be. If this is the radial direction, when we take a time derivative for that unit vector, the new unit vector should be pointing 90 degrees away from that, so that would be the transverse direction, and we should also have a theta dot. And there you go, we have a theta dot and it's pointing in the transverse direction when we take the time derivative. We already had an r here from using the product rule, so the radial component for the velocity, the transverse component for the velocity is going to be r times theta dot, and the radial component is just r dot. I don't really like how they write this as 2 different equations in the textbook, which is why on my equation sheet I wrote the velocity here we go, like this, which, oh, I guess that's, because this is for cylindrical components, so here we go. I like to write it this way because what they're telling you here is obvious. If you're looking for the velocity, it would be the radial component in the radial direction plus the transverse component in the transverse direction, and this is the more important part, what the radial component is and what the transverse component is. But why not just put it all together in one equation, which gives you all of the information that you need. Okay, so that's for polar coordinates, and then for acceleration, you'd have to take the time derivative of velocity, and you have to use the product rule for that. This is coming from what we have here without the z component, and so now you're taking the time derivative of this using the product rule, so we have r double dot in the radial direction, and then you have to use the product rule, so now it's r dot times the derivative of the unit vector here, and then for this term here, since we have three terms, we have to use the product rule and say time derivative of r times theta dot times the unit vector, and then time derivative of theta dot, which is theta double dot, in this term here, and then time derivative of the unit vector here. The time derivative of the unit vector that we have here, that's pointing in this direction, and by my little handout here, if we take a time derivative of this unit vector, the new one's pointing 90 degrees away from that in this direction, and then we take a time derivative of this unit vector, we keep going around in the counterclockwise direction, so the new unit vector is pointing that way, and we also get a theta dot, and so when we take the time derivative of our unit vector here, we have a theta dot, and the negative sign comes because they say u sub r here, which is pointing this way, and I said the unit vector should be pointing that way, so we get the negative sign there. And so if we look at our acceleration equation, ignore the z component now, and we have r double dot minus r times theta dot squared for the radial component, and r times theta double dot plus 2 times r dot times theta dot in the transverse direction, and you can see that from the derivation on the page there. Okay, then they just talk about cylindrical components where you add the z component, but the z component for cylindrical coordinates worked the same way it did for rectangular coordinates. So we should be good there. So you can read through those pages on your own. You can also look at the example problems if you desire, and we will look at some example problems together in the next video.